We defined a field yesterday as a line of influence that surrounds something. A force is a push or a pull. There's a distinct relationship between a force and a field, however, including with gravitational fields and gravitational forces. You need to have an object to produce a field. You need to have something causing gravity, but you don't need something to experience it. You do need something to experience a force. You got to have something to be pulled in order to have a pull. Now, why did we invent the idea of gravitational fields, this concept of fields that is really a human-made construction, a human-made concept? The idea of gravitational fields helps us to understand the existence of gravity or the existence of something else, electricity, magnetism, whatever the case may be. In this case, gravity. The existence of gravity when we don't have that pull, when we don't have something experiencing it, when we don't have a force. Right now, the board marker is in my hand. It experiences a gravitational force that's caused by the field. But if I take that pen away, the gravitational force is gone. Gravity hasn't disappeared. The thing that causes the gravity is going to always cause the gravity as long as it's there. The Earth is still here. Although we don't experience a force because there's no pen there to experience it, there's still got to be gravity there. How do we describe it? This concept of fields describes gravity or electricity or magnetism or whatever when there's nothing there to experience it. So, bottom line, in order to have a field, just the potential to influence something, the potential to cause a force, in order to have a field, you've got to have a producer. You've got to have something causing it. In order to have a force, which is the actual push or a pull, in gravity's case, a pull, you've got to have the producer, whatever it is that's causing it, but you've also got to have the experiencer, something feeling it. You can't have a pull without having something to be pulled. We talked about gravity fields as being vector fields because they have a direction. Right? The gravitational field always points toward the producer. If this is the Earth, then the gravitational field that's caused by the Earth is always pointing towards it like this. That means it influences objects with mass. A ball, a brick, a rock, a car, a person. It always influences objects to fall downwards toward the center of that object, toward the center of the Earth. The gravitational field influences in a particular direction. It's a vector field. All right? Now, we also introduced 3 equations yesterday. The first one wasn't a new equation, and it really wasn't even a gravitational field equation, but I'm going to write it down again because it's related to gravitational fields, and you'll see how it is in just a couple of moments. The first equation was the gravitational force, G m1 m2 over r squared. It's the force between any 2 objects with mass, the ball and the Earth that you saw in the diagram a second ago. It's the gravitational force between the Earth and the Sun. It's the gravitational force between you and the person sitting beside you. Gravitational force, not field, gravitational force. Now, the next equation was new. The next equation said G is equal to big G, m over r squared. This is what we call the producer equation for fields. Little g is gravitational field. If we have information about what produces the field or what causes the field, then we're going to use the producer equation. If, on the other hand, that would be the Earth, by the way, in the pen Earth example. We know something about the Earth. Let's use the producer equation. If, on the other hand, we know something about the pen experiencing the Earth's gravitational field, then let's use the experiencer equation. It's F over m. M in this case would be the mass of the producer, and m in this case would be the mass of the experiencer. R in this case would be the distance from the producer, the distance from the center of the producer, and F in this case would be the force of gravity felt by the experiencer, or you could say the weight of the experiencer, right? Force of gravity is weight. The force of gravity felt, or the force experienced by the experiencer. And of course, it's going to be in newtons. So how do these two things relate to the first equation that we wrote down, the force equation? Here's the Earth, or any other object with mass that produces a gravitational field. Here's the field that surrounds it, always points towards it. Here's an object out here with mass. It's a ball, it's a rock, it's a meteor, whatever it is, it's a certain distance from the center of the Earth. The Earth produces a gravitational field, G, at that point. The rock, the meteor, the ball, the spaceship experiences a gravitational force field, G, at that point. The field that's produced by the Earth is the same as the field that's experienced by the ball. If that's the case, then there's no reason why we can't set those two equal to each other. We don't very often do that, but we can. The field caused by the producer is equal to the field experienced by the experiencer. Hey, let's sub in an equation here. Gm over r squared is equal to F over m. Let's rearrange this. Solve for F. It becomes G times m. One of these masses is the mass of the producer, one's the mass of the experiencer, divided by r squared. You recognize that? It's Newton's law of universal gravitation, the gravitational force equation. So they're very closely related to each other. The field experienced by an object is the same as the field that's produced by whatever it is that caused it. And if we set those equal to each other, we end up with the gravitational force that acts between those two objects. All right. We're going to go straight to an example question from this. Okay, this is pretty much where we finished up yesterday. We just didn't have time to do an example, so we'll do that now. By the way, this is your quiz tomorrow. Okay, five of these numbers will be on your quiz. I'm not going to tell you which five. Just memorize all of them, and then be prepared to regurgitate five of them, any five of them for me tomorrow. Okay, got that? Phil, you okay with that? Good. All right. Here's the first question. We're going to refer to this table, which, not tomorrow, okay, because next you're going to have that table memorized by tomorrow, right? Guys, obviously we don't have to know those numbers. Okay, if we ever need a number from that like we do in this question, we're going to have the table there, or we're going to have the information given to us in some form. Okay, we never have to memorize any of those numbers. Question A says, calculate the magnitude of the gravitational acceleration of an object at the equator, on the surface of the Earth, and on the surface of the Moon. What's another word for gravitational acceleration? What's another term for that we've learned over the last day or so? Gravity, you've got to be a bit more specific than that. The gravitational field. So we're looking for the acceleration due to gravity. That's what you would have called it on the third day of class this semester. Now we're calling it gravitational field. It's really the same thing. Okay, it's little g. We want to find it at the surface of the Earth and the surface of the Moon. What do you know more about? The Moon, the Earth, or the person on the Earth? Which, by the way, strikes me in two ways. First of all, this person is very, very large. Second of all, this very large person, seems to be standing in the middle of the ocean and somehow not sinking. You would think a person that heavy would sink into the ocean, but they're not. Okay, they're not. Could be. What do we know more about? The Earth or the person standing in the middle of the ocean? The Earth is what causes the field. The person experiences the field. We know more about what do we know about the person?
She looks like a female, is wearing a pink shirt. Nice tan-colored pants. I can't really tell the shoes, but I like the look, really.
You do, eh?
Yeah.
Yeah. Do we know anything else besides the color of the shoes and shirt and pants?
She means...
I'm not even sure it's a girl. Is it a girl? Long hair and pink. Never know, right? Can't guarantee. Nope. Stereotypes, man. Listen, we know nothing about the person that's on the surface, really. We know nothing about that person, right? Do we know anything about the Earth? Well, not in the question, but if we refer to the table, we do. We know the mass of the Earth is 5.97 times 10 to the 24, and we know the radius of the Earth. The radius of the Earth is the distance from the center of the Earth to wherever this person is. That's the number we want, the distance from the center to where the person is. So let's use the producer equation because we know something about the producer, the mass and the radius. 6.67 times 10 to the minus 11 times the mass of the person, which is, of the Earth, which is 5.97 times 10 to the 24, and divided by the radius, 6.38 times 10 to the 6. Let's put brackets around that and square it. When you do that math, you should get a number that's about 9.78. We could say newtons per kilogram, or we could say meters per second squared. Either one would be okay. Meters per second squared is what we're used to. Newtons per kilogram is kind of the new unit for gravitational field or acceleration due to gravity. Now this is the field strength surrounding the Earth, on the surface of the Earth. What about the moon? I'm going to go through the same process, but I want you to make a prediction first. The moon is lighter, but it's also smaller. Are we going to have a gravitational field that's bigger or a gravitational field that's smaller than that caused by the Earth? Yep. Why do you say bigger? Okay. Yep. Okay, so it's still got a big mass, not as big as the Earth, but still big, right? 10 to the 22 kilograms. It's got a smaller radius and therefore a smaller volume and therefore higher density. Maybe higher density. Depends upon that combination of mass and volume, right? Bottom line is right now, we don't know. If mass was bigger and radius was smaller, no question, field strength would be bigger. If mass was smaller and R was bigger, no question, G would be smaller. But since one causes an increase and one causes a decrease, which one acts more, we don't really know yet. Let's calculate it and see. 6.67 times 10 to the minus 11 times the mass, which I don't remember what that is. The mass of the moon is 7.35 times 10 to the 22. Divide that by the radius of the moon. The distance from the center to the surface is 1.74 times 10 to the 6, which we got to square. We do the math there, and I think it worked out to be 1.60 newtons per kilogram, or 1.60 meters per second squared. So the field caused by the Earth is stronger, quite a bit stronger actually, than the field caused by the moon. Okay, we have a difficult time predicting that because of that balance, right? That balance is kind of trying to be struck there.
How many planets do you have?
But, oh, about the Earth, just probably the Earth would be about it. Yeah. How do you find the mass of the moon and the Earth and stuff? Yeah, that's a good question. That's a good question. I'm sure there's more than one way of doing that. But one way that I'll point out to you is this. Remember this? Kepler's third law, that third law that said Kepler's constant for the central body, that's, we'll say the sun that's being orbited around, is equal to t squared over r cubed for the Earth. That's not a radius of the Earth, but a radius of revolution of the Earth, okay? Yeah, you're looking for the actual radius of the planet, eh? Okay, or the actual radius of the moon. Okay, so, sorry, I'm kind of misunderstood your question there for a second. This would get you the radius of the orbital path. Say you got information about the Earth, great, get this, and then set that equal to, say, Mars. Got this now, and maybe you got the time that it takes Mars to go around the sun, find the orbital radius of Mars. That's not the radius of the actual planet. How would you find the radius of the actual planet? Probably by observation, to be honest. I mean, you know, if we know a distance that the planet is away from us, Okay, then you could measure the size of it and use some mathematics to determine its radius. And if we know its radius, we could determine its volume. Okay, and if, yeah, I don't know, beyond that, mass, I'm not sure. Maybe by a density calculation, maybe. Yeah, I'm not sure exactly, actually, but something like that, probably. Hey, one more thing that they were asked for here in question B. It says, what's the ratio of G to G, the gravitational field on the Earth compared to the gravitational field on the Moon? What does ratio mean? What's another word that means the same thing as ratio? Yeah. You could express a ratio as a percentage. I wouldn't say that it necessarily means the same thing. I'm thinking of a word, compare, ratio, compare. We see those words a lot in Physics 30, actually, where we want to find a ratio or we want to compare two things. If they're numerical comparisons, how are we going to do that? How are we going to compare them? Well, there's a number of ways we could. Some of you guys are 16, some of you guys are 17. Who's 17 here? Okay. Let's say that, Matt, you were 17? Okay. Matt's 17. Let's pretend for a second that I'm 34 for ease of calculations. Jonathan's smiling there. I don't know why he's smiling. I don't know why he thinks that I might be more than 34. Another year or two, I'll be 34. So Matt was 34. Sorry, Matt was 17. I'm 34. Let's compare my age to Matt's age. How do you compare those two? What's one way of comparing them? Yeah. We could divide them. We could say I'm twice as old as Matt, right? That's a good way of comparing. It's a legitimate way of comparing. What's another way of comparing our ages? How about subtracting them? To say that I'm 17 years older than Matt, is that a good way to compare them? Sure, that works. It's not as good a way as dividing, though. Dividing is a better way. Here's why. When Matt was 1, I was 18. I was still 17 years older than him, but I was 18 times older. I was 17 years older, but 17 years when he's 1 and I'm 18 is a really, really big difference. Now he's 17 and I'm 34. I'm still 17 years older than him, and that's still quite a difference in our ages. But it's not nearly as big of a difference, it seems, as when he's 1 and I'm 18, right? Now, when Matt's 90 and I'm 107, and we're both in the same home, yeah, hanging out playing bocce ball on the back lawn of the nursing home, calculating the orbital radius of Jupiter in our spare time, then, hey, he's 90, I'm 107, who cares? It's just about the same, right? 17 years doesn't make much of a difference at that point, right? We're both old. Okay, we're both within 20 years of kicking the bucket there, Matt, right? Okay. Maybe a little bit, when I'm 107, maybe a little bit closer than you are, but maybe a couple hours, yeah. The point is, when we subtract them, it is a way of comparing, but it's not the best way because it's relative to what each of the numbers are. If I divide the two, okay, when I was 18 and he was 1, then the ratio is 18 to 1. That's a big difference. Now it's 2 to 1. That's still quite a difference, but not nearly as big as it was when Matt was 1 year old. Okay, when I'm 107 and he's 90 years old, then, what's the ratio? It's almost 1 to 1, right? What we want to do when we want to find a ratio or compare is divide. Remember that. Ratio, compare, divide. 3 words that mean the same thing. Ratio, compare, divide. Just like I divided 34 by 17 to get the ratio of my age to Matt's age, I want to divide 9.78 by 1.60 to get the ratio of the field caused by the Earth to the field caused by the Moon. We end up getting 6, by the way. If the ratio of our ages is 2 to 1, Matt, then the ratio of the fields is 6 to 1. Is that okay?
You always divide the bigger number by
Good question. No, you don't. That's a good question, Nick. Do you always divide the bigger number by the smaller number? No. You always divide the one that's mentioned first by the one that's mentioned second. You want to find the ratio of the Earth's field to the Moon's field, Earth's field divided by Moon's field. If you want to find the ratio of the Moon's field to the Earth's field, then it would be 1.6 divided by 9.78. Is that okay? We see that quite a lot in Physics 30. The ratio, compare. What do they mean? One word, the D word, divide. Got it? All right, take a look at these questions that go along with that. Page 218, number 1 to 3. Let's take a look at one more example here. It says, what's the mass of a 60-kilogram student on Mars and on the Earth? Okay, this is an easy question. Don't make it harder than it has to be. What's the mass of a 60-kilogram student on the Earth? 60 kilograms. What about on Mars? 60 kilograms. Now, the force of gravity is different, the weight is different, but the mass is always going to be the same no matter where you are in the universe. Your mass doesn't change. What's the student's weight or the force of gravity felt by the student at the equator of the surface of Mars and of the Earth? There's two ways to handle this one. We know something about Mars and the Earth. Let's find the gravitational field that's caused by the Earth. Once we find the field that's caused by the Earth, we can take that from the producer equation and use the experiencer equation. So the field caused by the Earth can be plugged into the field experienced by the person. We could turn around and solve for force. Done. That's the force of gravity. Now, the other way to handle this is to say, look, if I'm going to use the producer and the experiencer equation together, and I want to find force, why don't I just use that first equation that I gave you at the beginning of this lesson for gravitational force? Why don't we just say F is equal to gm1 m2 over r squared? Didn't we say that when we set this equal to this, we end up getting this one anyways? Let's just solve for the gravitational force using Newton's law of universal gravitation. If you don't notice that, it's okay to use fields. It's okay to find the field strength caused by the Earth and then the field strength experienced by the student on the surface of the Earth and then set them equal to each other. Okay, and do the same thing for Mars. Or we could just go to this equation right away. Is that okay? I'm not going to bother finishing solving this. I'm going to allow you to take the last 5 minutes remaining to just work on the problems to give you a little bit of a leg up on that. But if anybody has an issue with actually solving this, just let me know and I'll help you out with it. All right? So we've got 218. We've also got page 220. That's it for today.